This is the 23rd lecture in the course Signals and Systems, and we are going to talk more about sampling. If we recall what we did last time, we had a continuous time signal x of t, and what we did was we multiplied this signal by a sampling function p of t. This is the symbol for a multiplier, x of t and p of t, and the sampling function was an impulse sampler, that is, it was delta of t minus nt, where n goes from minus infinity to plus infinity, and the result we called this, let us say, xp of t, and the result was simply a sequence of impulses whose strengths are equal to the value of the continuous time signal at that particular instant. In other words, if my xt was something like this, if my xt is something like this, then xpt shall look like this. It is a sequence of impulses at regular intervals, and if this is, let us say, t equal to 0, then the strength of this impulse is x of 0. If this is capital T, then the strength of this impulse is x of capital T, and so on and so forth. So this is, this green arrows show what the sampled form of x of t is, that is xp of t. I must point out here that an impulse sampling is not realizable in the laboratory. You cannot realize an impulse. What you can realize is a narrow pulse of large height, and as you know, the impulse is approximated like this. If the height is 1 by delta and the width is delta, then as delta tends to 0, this pulse becomes an impulse. So in actual practice, what we do is we sample with rectangular pulses of very narrow width. You shall see later on in your course in communications that this amounts to very little distortion if delta is sufficiently small. As far as the spectrum is concerned, the resulting spectrum, the spectrum when a function is sampled with a sequence of pulses like this, is simply the spectrum of ideal impulse sampling modulated by a slowly varying spectrum, which for all practical purposes can be ignored. Now after this, what we argued is that the spectrum of xp of t, that is capital xp of omega, it becomes simply a periodic repetition of the spectrum of capital X of omega. This stands for capital X of omega, that is the original spectrum, and then in xp of omega all that we get is a periodic repetition of this. There is a point that I want to make, lest this be misunderstood, that not all spectra are like a triangle. It is simply an example that we take. It could be the actual spectrum could be something like this. We don't care. All that we care is two conditions, that is x of t is band limited. That means whatever the shape of the spectrum, there is an upper frequency omega h in the spectrum, okay, beyond which the spectrum is 0. That is, all the energy of x of t is contained within a finite band of frequencies. So xt is band limited, and the second condition that we derived from this particular diagram was that the sampling frequency must be greater than or equal to twice omega h. These are the two conditions. Then we argued, under this condition we argued, yes.
So last time when I had asked, why don't we impose a condition on omega L?
On omega L,
so
yeah.
I can get what exactly it is.
We will discuss this point. Is there a limitation on the lowest frequency? Here the lowest frequency is shown to be 0. Is there a limitation on lowest frequency? No, there is no limitation. Basically, you can have from right from 0 to any upper frequency that you want. But there are cases in which the lower frequency is automatically limited. In other words, we have signals which are band pass signals rather than low pass signals like this. All right, that is signals whose energy content is limited from a non-zero lower frequency to a finite upper frequency. What do we do in that case? We shall illustrate at the end of this class with the help of an example. I remember your question. We shall consider this. In fact, I found out an example in the text which deals precisely with this particular question. We shall come back to this later. Yes.
So suppose we are just given the sample version of any signal.
Yes.
And we are asked to find its spectrum. We don't know what the original signal is. We just know the sampled version of that. Then how do we construct its spectrum?
Correct. We only know the sampled version of the signal. That is, we are only given the samples, right? We are only given the samples. Okay. The question is the following. Suppose we are given samples of a particular signal. How do we reconstruct?
Construct its spectrum. Just its
How do we construct its spectrum? Well, you have to take its Fourier transform. The question is, if this is given, let's say x of 0, x of capital T, x of 2t, x of minus t, x of minus 2t. The question is, how do we construct its spectrum? Well, we take the Fourier transform.
So, but Fourier transform is always unique of a given function. But if we take two different types of signal whose sampled version is same, we'll get two different spectrums, and both of them correspond to the spectrum of the sampled version.
Well, this is the essence. The question is, if we have a signal whose samples are this, the signal is not necessarily unique. Alright, we can have two signals, as we illustrated last time, two signals having the same sampled version. Well, the sampling theorem says that if the sampling frequency or the sampling interval has been chosen with due regard to the highest frequency content, then the reconstructed signal should be unique. In other words, you don't lose any information. The spectrum is intact means if the spectrum is intact, that is, if x of omega is not changed, naturally x of t has also to be unique, because the Fourier transform and the inverse Fourier transform, they offer a one-to-one relationship, and therefore the answer shall also be unique, provided you have paid regards to the sampling theorem. That is, you have chosen the sampling frequency accurately. Well, how to reconstruct the signal given these samples is another problem, and that problem is called the problem of interpolation, which we shall come to a few minutes later. All right, but it is true that if you are given the signal only, then you know the sampling frequency. If you know the 0 capital T 2t, the interval, then you know the sampling frequency, and you can find out its spectrum and see if the spectrum. How do you know whether the sampling frequency has been chosen correctly or not?
There is no overlap.
There is no. You have to find out whether the spectrum has an overlap or not. If the spectrum can be divided into distinct samples, distinct regions, separated omega s apart, and omega s you know, capital T. 1 by capital T is Fs, 2 pi Fs is omega s, and therefore if you can separate the spectrum into blocks which are separated by omega s, then you know the sampling frequency. The sampling theorem has been obeyed and the sampling frequency has been chosen correctly. Alright, let's go ahead. Now, this question of impulse sampling, let's represent it once more by this diagram. We have a p of t, and what we have is xp of t, and we argued that if the spectrum, if the sampling theorem has been obeyed, then the spectrum is a periodic repetition like this, centered at omega equal to 0, omega equal to omega s, omega equal to minus omega s, and so on and so forth. And to be able to recover, this is xp of omega, capital xp of omega. To be able to recover, all you need is, you need a low pass filter whose cutoff frequency, a low pass filter something like this, whose cutoff frequency omega c lies between omega h and omega s minus omega h. Alright. So, omega c has to be greater than equal to omega h and less than equal to omega s minus omega h. In practice, this is also not a realizable function. An ideal low pass filter, it can be shown that it's a non-causal function. It's a non-causal system, and so it cannot be realized. So, in practice, there is an approximation to the ideal low pass filter also, and there can be a source of distortion. So, the sources of distortion in a practical sampled system can be three. Number one, an ideal sampling is not obtained, cannot be obtained, ideal impulse sampling, because an impulse cannot be realized in the laboratory. All you do is you take narrow rectangular pulses. Number two, the spectrum of no signal in the world is band limited. The spectrum of no signal in the world is band limited. There are always tails, trailing edges, which cause distortion. And number three, a low pass filter which is used to isolate or to recover the original signal, well, an ideal low pass filter cannot be obtained. So, the limitations are on what did he say? First, no delta function. No delta function can be realized in the laboratory. Number two, omega h in practical signals tends to infinity. There is no band limited signal. And the third is ideal LPF cannot be realized. And therefore, in practice you shall have distortion. And the distortion that one has to bother about is if the basic spectrum or the base band spectrum, the spectrum around omega equal to 0, which is the original, which is the spectrum of the original signal x of t, if this overlaps with the next repetition, then we shall have a distortion which is very serious, and this is called the aliasing distortion. The term had been introduced earlier. If we have a situation like this, this is the baseband spectrum, and then the next spectrum repeats like this, that is omega s has not been chosen correctly, then the overall spectrum becomes like this, and no amount of filtering, however carefully you do, shall be able to recover the original spectrum. In other words, the message or the information content of the signal has been disturbed, and therefore there is distortion. And this distortion, as I have already said, is the so called aliasing distortion, and the name arises because high frequencies pose as low frequencies. This point for example, it's actually a higher frequency. At this frequency, for example, it's actually a higher frequency, it should have come here, but it is posing as a low frequency, and low frequencies pose as high frequencies, and this is the source of distortion called aliasing. And once aliasing occurs, you can do nothing about it. The spectrum or the sampling has gone in vain. You cannot recover the signal. All right. Now, since ideal impulse sampling cannot be obtained in practice, are there simpler methods of obtaining sampling? And one of the methods is the so-called ZOH. This is a method of sampling, and the full name for this is zero order hold. And it's an extremely simple concept. Suppose you have an x of t. Suppose you have an x of t like this, let's say. Then you construct a device which gets stuck at the value, let's say at some point of time, let's say minus capital T. At some point of time minus capital T, the it could be a simple RC network, for example. The capacitor charges to this value of the voltage, all right. Then the signal is disconnected from the capacitor. That is, the capacitor voltage remains constant till it comes to the next sampling point, that is 0, at which the capacitor is again connected to the signal, and therefore the capacitor charges to the current value of the signal. Then it remains at this value till the next sampling instant comes, at which the switch is put on again, and therefore the signal goes up to the current value. It remains like this, then it reaches this value, it goes like this, and so on and so forth. You see what I mean? What I mean is, we have a signal source, let us say x of t, and there is a switch which closes every capital T instant of time, all right. It closes for a very short time, then is put off. Another capital T seconds later is put on again, kept on for a short time, and then again put off. And you have, let us say, a resistance and a capacitor, all right. Or this resistance has to be very small. It is a switch resistance, if you like. So what is happening is, when it is put on, the capacitor charges to the instantaneous value of x of t. Then it is put off, so the capacitor maintains its charge. When it is put on again, the new value of x of t is taken over by the capacitor, and so on. So it is called a zero order hold. It holds the value of the signal at the value which was existing at the previous instant, till a new value arrives, all right. So what we get is, if we have a signal like this, I am showing, then what we get is a staircase like this. And so on, where this interval between two stairs is capital T. This violet zigzag diagram is a coarse sampler. This can be used as a sampled version of the signal. Ideally, of course, a sequence of impulses, but this can also be used as a sampled version of the signal. Suppose this has occurred. Suppose we have an x n1 of t, let us say, this is x of t, let me use this color, and the violet one is x1 of t. x1 of t is the ZOH of x of t. It is the zero order hold version of x of t. Is there a way that we can recover x of t from x1 of t? Obviously, what is happening is, x1 of t is a rippled version of x of t, and this ripple obviously represents high frequencies as compared to the original signal. Original signal varies slowly, whereas this varies rapidly. So this represents a high frequency superimposed on the original signal, and qualitatively you can see that a low pass filter can do the job, should be able to do the job qualitatively. Let us look at it a bit quantitatively, and for that purpose let us consider a system, let us say h naught of t, whose impulse response is h naught of t, and let us say h naught of t is like this, 0 to capital T, h naught of t, and the value is 1 here. Let us consider a system with an impulse response like this. That is impulse response, that is, if fed with a delta t, then the output is h naught of t, which looks like this, all right. Now can you tell me what will happen if the input is delta t plus delta t minus t? Let us say, just a second, let us say 1 and 2, let us say, just arbitrarily, 1 times delta t plus 2 times delta t minus t. Now what will be the response? H naught t plus h naught to h naught t minus t, which means that this rectangular block shall be displaced, shall be multiplied by 2 and displaced by capital T. So, what shall you have? You shall have something like this up to capital T, then at capital T it will go to 2, alright, then it shall remain a constant up to 2t, and that is it. This is what will happen. Now, don't you see that the ZOH version of x of t is precisely a sequence of such impulse responses, alright, and therefore it follows. If it does not follow, let me know. It follows that if x of t is impulse sampled multiplied by pt and then passed through a system whose impulse response is h naught of t precisely of this form, that is, it is 1 from 0 to capital T, this is h naught of t, then what is the output? Output is simply x1 of t, that is ZOH of x of t, alright. Is that clear? Alright. Oh, we are multiplying by pt because we are creating a sequence of impulses. This is the impulse sample version. If I pass it through a system having an impulse response h naught of t, then we get the ZOH version of x of t. The question now is, from x1 of t, is it possible to pass this signal through another linear system, let us say HR of t, where R stands for recovery, alright, the subscript R stands for recovery, that is the impulse response of the recovery system, such that the output is x of t. Is this possible? The question is this possible? In other words, if I draw the complete thing, if I draw the complete thing, x of t multiplied by pt passing through h naught of t, then through what? HR of t, the output should be x of t. This is what I want, and I want to find out HR of t. You also recall that if we had simply x of t impulse sampled by p of t, then what is this xp of t? The spectrum of xp of t is simply a periodic repetition of the spectrum of x of t, and all we had to do to recover x of t was to pass it through an ideal low pass filter. Let us say its impulse response is h of t in such a manner that its frequency response, that is capital H of omega, was constant 1 from minus omega c to plus omega c, where omega c lies between
2 omega h and
no, lies between omega h and omega s minus omega h, right? So, and what is the output of such a system? The output of such a system is precisely x of t, alright, and therefore the requirement on HR of t is such that this cascade should behave exactly the same way as this block of h of t. Isn't that right? And therefore, our requirement is, for recovering this signal, our requirement is that h naught of t convolved with HR of t should be equal to h of t, alright. And in other words, what we get is h naught of omega. If I take the Fourier transform, then h naught of omega multiplied by HR of omega should be equal to h of omega, alright. Now, therefore, HR of omega, that is the requirement of the recovery system, is that the frequency response should be h of omega divided by h naught of omega. And you can see that h naught of omega is simply the Fourier transform of this, it is a sinc function. Therefore, H naught of omega is equal to, you see, it will be even if I shift it to the left by capital T by 2, and then it will be a truly sinc. Since it is shifted to the right, we have to multiply by e to the minus j omega t by 2, this you can verify, e to the minus j omega t by 2, then twice sine of omega t by 2 divided by omega. And therefore, the impulse, the frequency response of the recovery system is HR of omega. I will write it again. It shall be e to the j omega t by 2 multiplied by h of omega divided by twice sine of omega t by 2 divided by omega. This is the recovery system. Alright. Now, depending on h of omega, capital H of omega, I know what is capital H of omega. It is 1 from minus omega c to plus omega c, otherwise it is 0. You can find out h r of omega from here, and then you can find out h r of t. Alright. So, the recovery system, we can find out the impulse response of the recovery system. However, as I said, what kind of HR of t shall it be? Shall it be realizable? An ideal low pass filter is not realizable. It is a non-causal system, and therefore, if we multiply this by capital H of omega, it means that something is being convolved with H of t, a non-realizable or a non-causal system, and therefore HR of t shall also be non-realizable. Alright. However, good approximations to this can be obtained in practice, and we shall look at them later. Even a simple RC filter like this may do the job reasonably well, provided your frequency content is not too high. Alright.
Sir?
Yes.
So even if somehow you were able to realize the ideal low pass filter, still the system which you have constructed, so of what use it is, because that omega c is not some fixed value. Omega c will depend upon the
highest frequency,
on the highest frequency of the sample signal.
That is correct.
So I mean, therefore different signals will have to make different systems.
That is quite correct. It is application specific. The low pass filter, the choice of the low pass filter, the cutoff frequency and the shaping characteristic will be application specific. What application? What is the shape of the spectrum? How far does it go? What is the shape of the cutoff slope of the low pass filter? All this will depend on the application at hand, and there has to be, these systems are all dedicated systems. You cannot make a universal system. Alright. The next question that we consider is the question of reconstruction. Well, one of the things that we have already discussed is that if we have an xp of t, that is the sampled version of a continuous signal, what we have to do is to pass it through h of t, where h of t is an ideal, is the impulse response of an ideal low pass filter, and then we get x of t. Now, there are too many ideal things in this. First is that xpt is already an idealized concept, because an impulse cannot be realized. H of t is not realizable. It is the impulse response of an ideal low pass filter, and therefore there is a lot of non-idealness involved in this. However, even with this non-idealness in practice, it is instructive to find out an exact formula for reconstruction, which we shall do in a moment. That is, we want to relate x of t to h of t, x of t to h of t, and its sampled version, that is x of nt. We will do that in a moment, but let us look at some of the simpler concepts. That is, suppose we are given a sequence, a sample sequence like this. Okay, and we want to reconstruct the original signal. Well, one of the things that we can do is we subject this to a ZOH. a zero order hold, which means that we make a system in which this sample charges a capacitor, the capacitor charge remains constant till the next sample comes. When the next sample comes, the capacitor rises in voltage, then it remains constant up to the next sample, then it loses charge so that it reaches this level, then this level remains constant till the charge becomes, till the next sample comes, the charge becomes negative, and then this remains constant till the next one, and it goes up like this, then it remains constant, and so on. We can apply it to a zero order hold, and then this zigzag version we can apply a low pass filter to it and have a recovery of the original signal to a reasonable degree of accuracy. This is, so a zero order hold is also an interpolator. That is, what we are essentially doing is we are interpolating the value of the signal between two sampling instants. Only a part is given, only these are given, these blue samples, these are given. In between we have no information. So in absence of information, all we do is we assume that the signal remains the same as at the previous instant. So we are interpolating or we are approximating. This is called a zero order hold interpolator. Another thing that we can do is which is also common sense, that the signal is given at certain instants of time, and all we do is we join them by straight line. Alright, that is, we do this quite often in drawing graphs. We join the tips by a straight line. Okay, then this is an approximate representation of the signal. And such an interpolator, well, this could be a constant current charging of a capacitor. When you know the voltage rises linearly. Okay, there are corresponding electronic circuits which you shall learn later in digital electronics. This is called a linear interpolator. Linear interpolator. In the zero order hold, what is the transfer function? Transfer function, that is h, not transfer function, the frequency response, h naught of omega is of the form sine of omega t by 2 divided by omega. All right, and this, if you plot this versus omega, well, I want to make a point, so please follow this point carefully. For a ZOH, well, an ideal low pass filter is like this. Now that ideal low pass filter. For a ZOH, the frequency response function, which is sine omega t by 2 divided by omega, well, it looks like this. And you can see that this is an approximation to an ideal low pass filter. So ZOH is an approximation to an ideal low pass filter, and the more it deviates from the ideal low pass filter, the worse will be the reconstructed waveform as compared to the original waveform. On the other hand, if you take a linear interpolator Li, it can be shown, you can easily show this, it's a TUT form, it's a linear function, and you can show that the frequency response is of the form sine omega t by 2 divided by omega whole squared. What does it mean? It means that the slope of cutoff, that is the decay, will be steeper. That means if this is 1, 1 squared is 1, but 0.9 squared is 0.81. Where the response is 0.2, the square of that is 0.04, and therefore it falls much steeper like this. So a linear interpolator is a better approximation to a low pass filter, and these two are simple cases of low pass filtering or interpolation. Let's look at the exact interpolator. That is that is x of t is xp of t is given to an ideal low pass filter h of t, and we get x of t. You recall that xp of t is nothing but x of t multiplied by summation delta t minus nt, n equals minus infinity to plus infinity. That means this is equal to summation x of nt. I can take x of t inside the summation delta. It's important to recall this, although it looks trivial. I have done this many times. xp of t is this form. Now what we are doing is x of t is xp of t convolved with h of t, and if this convolves with h of t, all that shall happen is that the delta shall be replaced by what? Now it's not clear. This function is convolved with h of t. Then x of nt is a constant as far as the convolution is concerned, and therefore all you are convolving is ht with delta t minus nt. So delta t minus nt shall be replaced by h of t minus nt, and therefore all that we will get is x of t shall be xp of t convolved with h of t, and therefore this shall be x of nt, which are the samples, then h of t minus nt, n goes from minus infinity to plus infinity. So in this exact reconstruction, you need the samples of x of nt, which is the sequence that is given. All you need is the impulse response of the ideal low pass filter. That is, if I have a filter like this, minus omega c to plus omega c, and let's say this is 1, then by inverse transformation you can show that h of t is nothing but, it's a sinc function, it is omega c t by pi. It's very easy to show by integration. H of t 1 by 2 pi integral minus omega c to plus omega c 1 multiplied by e to the power j omega t dt. dt or d omega? D omega. Right. So what you get is omega c t pi sinc of omega c t by pi. This is the formula. And you can see that h of t is not equal to 0 for t less than 0. Isn't that right? And therefore this is a non-causal system. Alright, and therefore my x of t becomes summation x of nt, n equals minus infinity to infinity. Then we have omega c t by pi. This remains a constant. The only thing that happens is h of small t minus nt. So sinc function of omega c small t minus nt divided by pi. This is my final formula for exact reconstruction, and this in the literature goes by the name of interpolation formula. I must emphasize that this is an exact reconstruction. Exact reconstruction naturally is not possible because this system h of t is unrealizable. Do you recall the definition of sinc x? Sin pi x divided by pi x. Okay. That is sine of this divided by sine of pi times this divided by pi times that. This is why pi occurs here in the denominator. All right.
Sir.
Yes.
So omega c can be any value in the interval omega h and omega s minus omega h.
That's correct.
So then we can choose so many different values for omega c.
Correct.
So will we get the same thing?
You will get the same thing because there is no spectrum outside this. Omega h minus omega h. So whether your filter is like this or your filter is like this, it doesn't matter. It only accepts this spectrum. So it's independent of omega c, provided omega c satisfies those constraints. You're quite right. A good point. Now we go to the question that was raised regarding the lower limit of spectrum for sampling. I found out that in the textbook there is a problem P8.6 which deals specifically with this problem, and it's extremely instructive to consider this problem in a little more detail. What it says is, consider a signal whose spectrum is like this. This is capital X of omega, alright, versus omega, where this is omega 1, this is omega 2. This is the lower frequency end is limited to omega 1. This is minus omega 1, this is minus omega 2. Alright, this is the spectrum, and this is given. The question is, what should be your sampling frequency? What is the minimum value of the sampling frequency? Obviously, Nyquist's sampling theorem states that omega s should be at least twice omega 2. Isn't that right? The highest frequency content is omega 2, so twice omega 2. And it appears unfair that a signal whose energy is concentrated between omega 1 and omega 2, a rather narrow band, you require such a large sampling frequency, because all this is blank. There is no energy of the signal here. It appears therefore justified to at least qualitatively predict that perhaps a lower sampling frequency should do, and indeed it does, as we shall see now. What we do is, we don't derive this absolutely rigorously at the point. We go more from a qualitative point of view, and we arrive at the same result. What we do is the following. Suppose this is the spectrum of x of t, and we multiply it by p of t, where p of t is a sequence of samples like this, and capital T for the moment we keep it unspecified. All right, we don't know what capital T is. Let us see what capital T should be. Let us try to find some restrictions on capital T such that we can recover the original spectrum. All right, capital Pt is the sampling function. Now, if I do that, if I multiply x of t by p of t, well, what happens is the spectrum becomes like this. Omega 1 to omega 2 and minus omega 1 to omega 2. This is centered around 0, and therefore there will be a repetition of this centered around omega s, some omega s. Let's say this is omega s. Then around this there will be repetition. In other words, there would be something like this and like this. Okay, it may not have been very accurate drawing, but you understand what I mean. This frequency, what will be this frequency?
So
omega s minus omega 1.
Omega s minus omega 1, and this frequency shall be omega s minus omega 2. Obviously, omega s has been chosen correctly, okay, so that there is no overlap between the spectra, the repetition spectrum. The spectrum also repeats on this side. It suffices to concentrate on the first periodic repetition. Suppose what will happen if capital T is increased? Capital T increased means omega s decreases. All right. If omega s decreases, then what will happen to this figure? It will shift to the left, and if it shifts in such a manner that it occupies a position like this, let's use a different color. Suppose it occupies a position like this, then obviously aliasing shall occur, because the two spectra have overlapped with each other. All right. But suppose we shift it beyond this, follow this carefully. Suppose we shift it like this. Suppose we shift it like this. Then obviously there is no overlap. Isn't that right? So it is possible to choose a capital T such that this spectrum is shifted beyond this basic spectrum towards the origin of the frequency axis, and we shall avoid no aliasing if
omega 1 is greater than half omega 2.
Okay, first the lower end, omega s minus omega 2.
Less than omega 1.
No, the lower end.
Less than minus omega 1.
Greater than minus omega 1.
Greater than minus omega 1.
That would be the upper end. That is omega s minus omega 1. The upper end must be less than omega 1. What is the restriction omega s minus omega 2?
Greater than minus omega 1.
Greater than
Minus omega 1.
minus omega 1. Well, there is a problem. If this shifts here, what happens to this one? This shifts here? Isn't that right?
Little shift there, sir.
Well, this has shifted here, and therefore, see, this is omega s minus omega 2. Therefore, the other one will shift towards the origin. It has to shift symmetrically, and therefore we cannot shift this end beyond origin. Then again there shall be overlap. Isn't that right? So omega s minus omega 2 must be less than,
Greater than.
I'm sorry, must be greater than 0. Is this point clear? It's a very elegant theory that was arrived at simply from qualitative reasoning like this. And this is what is used in bandpass sampling. In bandpass sampling, you see, you must realize that we cannot sample a signal at any given frequency that we want. After all, sampling involves an electronic circuit, and electronic circuits have a limitation on how high a frequency, a given signal can be sampled. There is a limitation. You cannot sample at 1 gigahertz, for example. The stray capacitance, that will kill everything. You know, you think of a mechanical switch like this. When it is put on, it is on. When it is put off, it is off. But consider a frequency like 1 gigahertz. There is this very small stray capacitance. That makes a short circuit. It doesn't matter whether you sample or do not sample. It makes signal to pass even without a switch connection. Alright. So there is a restriction on sampling frequency. Now this shows that the sampling frequency, you can avoid aliasing if the sampling frequency is so chosen that omega s minus omega 2 is greater than 0, but omega s minus omega 1 is less than omega 1. Now you understand the limitation why this 0, because the other part comes and takes over. Alright, let's write this equation again, and then we shall have fun. Omega s minus omega 2 is greater than 0, and omega s minus omega 1 is less than omega 1, which means that omega s should lie between omega 2 and 2 omega 1. Now for this to be true, obviously the upper limit should be less than the lower limit. Upper limit should be greater than the lower limit. That is the restriction is 2 omega 1 minus omega 2 must be greater than 0. This is the only restriction that you apply to this signal. That is, the bandpass signal must be such that 2 omega 1 minus omega 2 is positive. Alright. If that happens, then what would your signal look like? Well, one thing is certain, that the minimum sampling frequency obviously is omega 2. Isn't that right? Omega s minimum is equal to omega 2. Is that clear? Omega s must lie between omega 2 and 2 omega 1. So minimum omega s that we can choose is omega 2. Where the sampling theorem states that it should be twice omega 2. You recall omega 2 was the highest frequency, and therefore the sampling theorem states that the sampling frequency should be twice omega 2. Whereas we have proved that the minimum can be omega 2. Now if it is omega 2, if the sampling frequency is indeed omega 2, then what does the sample spectrum look like? Let us see. The sample spectrum, we have chosen omega s equal to omega 2. So the sample spectrum would be something like this. It should, omega s minus omega 2 should be equal to 0, and therefore it goes like this. Alright, this is 0. And what would be this upper limit? It would be? Yes? Omega 2 minus omega 1, that is correct. Then we have omega 1 and omega 2, that is the original. Alright, then we have similarly on the other side, minus omega 1, omega 2. You recall that this triangle is the result of shifting this triangle to the left by appropriate choice of omega s. Now this picture is not quite what our original spectrum is. What is the original spectrum? Original spectrum is this. Original spectrum is this. Then we have superimposed on this by sampling this spectrum. Alright, a spectrum like this. Then we shall have a periodic repetition of this. So the question is, how do we recover the original spectrum?
To filter out.
Well, obviously we have to filter out this.
So first we can filter out the whole thing and then that whole thing.
No, we will do this filtering at once, at one step. What we will do is, we will filter out this and this, which means that our h of omega, the frequency response that is needed is let's say omega A, omega B, 1. Instead of a low pass filter now, we want a band pass filter, and therefore what we need is this 1 minus omega A minus omega B. And obviously the band pass filter will do if omega A is equal to omega 1 and omega B is equal to omega 2, right? Now you can have a little guard bed on this. Actually omega A does not have to be equal to omega 1. Omega A can lie between omega 2 minus omega 1 and omega 1. Similarly, between omega 2 and what will be the next point?
So it will start at omega 2 only.
Pardon me?
The next, it will start at omega 2 only.
It will start at omega 2. That is correct. That is correct. So we don't have a guard band here. We don't have a guard band. Omega B has to be equal to omega 2. And that shows one of the limitations of this kind of a sampling. Not quite limitation, but a practical wisdom. Your omega s should not be exactly omega 2. It should be slightly higher than omega 2. Omega s, as you recall, it should be greater than omega 2, less than what?
2 omega 1.
2 omega 1. And therefore omega s can lie anywhere between the two. And for practical separation, for practical ease of constructing a bandpass filter, your omega s should be slightly higher than omega 2, so that there is a gap here. Okay, between omega 2 and the next one there is a gap, and you can have a bandpass filter which passes like this. Is the point clear? Have I made it clear? There are many other forms of bandpass sampling. What we have treated here is one of the simplest, but it illustrates the point that the sampling theorem, as we have stated here, applies to, can you finish the sentence? What kind of signals?
Band limited.
Of course it is band limited. The bandpass sample is also band limited. The sampling theorem omega s greater than equal to twice omega h applies to low pass signals. A low pass signal is one whose spectrum lies between DC and a higher frequency, which is finite, 0 to omega h. A low pass signal is one whose energy is concentrated in the band 0 to omega h. On the other hand, well, it is only for low pass signals that we state the conventional sampling theorem. Sampling theorem is applicable to low pass signals. For band pass signals, the sampling theorem is not the same as this. We have taken one example to show that in a band pass signal, omega s can be as low as omega h, the highest frequency content. Alright, it can be as low. There are some other variations which you shall learn in the course on digital communications. And with that, we close our discussion on sampling. After the break, we will start with Laplace transforms.